Are we going? Okay. Well, welcome back, everybody. And as I say, if there are any questions at any point in the process, jump in. And if there's anything holding from last time, jump in as well. So I'm going to remind you sort of what we were doing last time. And I've got a couple of footnotes on the last lecture that I want to just mention before we dive into BPS equations and BPS conditions. Oop, my thing is, there we go. So let me remind you where we were. Basically, we're interested in looking at the following configuration. We have some D1 branes, some D5 branes. The D5s wrap a T4. The D1s and D5s have a common Y and T direction. And then there's a spatial transverse space, which is where we live, a spatial four-dimensional manifold transverse to it. And we're interested in the D1, D5, and a momentum wave traveling along that thing. And so the supersymmetry of this thing, first of all, the underlying theory is going to be that of the D1, D5 theory. So it's going to be reduced supersymmetry, and we talked about these supersymmetry projectors. And in particular, two of these guys imply that along the T4, when you look at the common direction 5, 6, 7, 8, 9, that it implies a holistic condition on epsilon. And similarly, a holistic condition in the six-dimensional space. This is why it's 2-0 rather than, or 1-0 rather than, it's the 1-0 supergravity rather than 2-0 or 2-2. The other thing also is when we throw the momentum in, we add in a momentum projector which goes along the common direction. Now, this first thing I wanted to observe about this is that when you combine it with the effects of these guys, this is the Holistian six dimensions. You combine it with this, it tells you on the 4 manifold that there's a further projection condition on your supersymmetries. And if you've ever seen anything like that before, it should scream at you hyperkähler. But we'll say more about that in a minute or two. So what I want to do is just talk about the supersymmetries of this configuration. And essentially, there is an SU2 cross SU2 action on the 4 torus. That's the tangent space symmetry. And similarly on the M4, there's a tangent space symmetry, which is SU2 cross SU2. So there are 4 SU2s on the go in this picture. And it's kind of important to keep them separated. And the usual labeling is SU2, 1, 2, and then left and right. This is because it's transverse to the whole stack of branes is actually the R symmetry. And this is some global internal symmetry that may not exist if you've got some other manifold like K3. But anyway, the spinor indices are going to be doublets, and so forth, A and A dot for the torus, and alpha prime for the space-time indices. And in principle, the supersymmetries for this lot, there are 16 of them, or if you put the internal 2B index on, there are 32, but there are 16 that I want to focus on. Basically, they have every kind of spinor index pairing that you have between this and this. And in terms of the representation structure, there are 4 SU2s, and here's their sort of doublet representations. That's before we put any projection conditions on them. But once you put the holistic projection condition on the internal space, it reduces you to the, kills off anything in this holisty, the A dot direction. And so as a result, it only leaves you with these supersymmetries. So I'm doing this because it's important to kind of know what the R symmetry is and what the global symmetry is and how the supersymmetries transform under this. So this theory actually has 8 supersymmetries that we're looking at. It's the 1-0 supergravity, but under this SU2, under the SU2s, one of them is doesn't transform under one of them. And it doesn't, and either it transforms under the left or right supersymmetry in the R symmetry space. And this defines the 8 supersymmetries. Now, when you throw in the momentum space projector, what it does is it kills off this guy. And it leaves you with only these 4 supersymmetries. These are the 4 supersymmetries of the configuration we're looking at. And you should notice that it's chiral on the left and on this sector. Now, what does that mean? Well, gamma 05 is not only the momentum space projector, but it's also the holistic projector on the common world volume 05 of the branes. And so what it's telling you is that you only can have one chirality of spinor. You get to pick. You can put a plus or a minus sign here. I think in the notes I put a minus sign. But that tells you that you must apply a holistic projector, either left moving or right moving. onto the supersymmetry that survives. And that makes sense because if you load up with a whole pile of left-moving states, momentum waves, then that is not going to be in the Ramond ground state, but the right-moving sector is going to be in the Ramond ground state. And therefore, this is the surviving supersymmetry, and it's right-moving, and it's chiral, associated with the right-moving sector, and it has an SU2 global symmetry. So one of the confusions here is if you tend to think of this theory as having an SO4 symmetry, and there's an obvious SO4 under which this transforms, but it's not the SO4, which is the SO4 of the transverse space. It's only one of the SU2s. The SU2 actually is right because we're piling up left-moving modes. And there's also a global symmetry index. So it's actually transforms as a doublet. It may be important later when we talk about it. Anyway, that's the 1-0 theory, and that's the footnote having to do with supersymmetry. The other thing that I wanted to point out is that, and we're going to see this today, that basically the 1/8 BPS condition leads you to this projection condition on not only on the 4 manifold, and that really is a statement about the fact that the 4 manifold you're living in should have something like, and I'm hedging my bets here because you'll see what I mean in great detail in due course. It says that the manifold should have some kind of SU2 holonomy. Well, really, it does have an SU2 generalized holonomy. This is telling you that basically only one of the SU2s is going to leave the spinor condition untouched. And so therefore, it's going to reduce the full spinor down to something which is the SU2 holonomy part. And so if it were pure geometry, if the space-time were pure geometry, then it would be a half-flat manifold, and you would have a high hyperkähler manifold on the transverse this space. However, because we've got non-trivial fibrations and fluxes, as we're going to talk about, then there are more general options. But just to set up the expectations, there is this all this D1, D5P supersymmetry tells you the transverse manifold has to have some special holonomy associated with that. And we're going to see that in great detail. Okay, so the other recap is to remind you what we're dealing with is we're dealing with 1-0 supergravity coupled to a collection of tensor multiplets. And we're going to deal with 0, 1, and 2 just to build up the problem progressively. And that means we've got gravitons. I won't care about the gravitinos anymore, but there's a graviton, there's a self-dual tensor gauge field, and a number of anti-self-dual tensor gauge fields, and the scalars and a coset. And we're going to look within this theory. This theory has 8 supersymmetries, and we're going to look for the half BPS states of this theory, which means 4 supersymmetries, or 1/8 BPS and 2B. Okay, so now we get down to it. What we're going to do now is to talk about what the supersymmetric geometries look like. But before I do that, any questions about where we started, where we're going, what the setup is? Any issues? Everybody's gone very quiet.
Can you quickly repeat, you mentioned something about the global symmetry after you said that there is just one SU2 remaining?
Yeah, it's because you're getting this thing, there's a torus in the compactification. And that, if it's a torus, then there's a global SO4 tangent space symmetry. Yes, it's reduced to a discrete group, but locally there is an SO4 rotational symmetry inherited from the torus. If you're K3, I think that's gone basically. But in the way I'm formulating it, there will be this extra accidental global symmetry in the way that a lot of these things formulate it. So basically things will transform under that SU2 global. And it descends to the supersymmetries. Is that answering Chris and Bogdan?
Yes, thank you.
Okay. So I'm going to start where the whole thing really started. There's this, the heavy lifting in this subject was done initially by Gutowski, Martelli, and Rial. All the references, by the way, I've typed up tech notes. All the detailed references, and a lot more than I'm going to give here, are in the references are in the tech notes. And the first part of this heavy lifting was all supersymmetric solutions, and the key word here is minimal supergravity in 6 dimensions, which means n equals 0. So no anti-self-dual stuff, the tensor gauge field self-dual. But the important point about this is he tells you, or that these authors tell you exactly how to build the appropriate geometry. So the very first thing you should know about this sort of story is that because you have commutator of two supersymmetries always gives you some kind of time translation. The presence of any kind of killing spin or supersymmetric solution means there's a time-like or null killing vector. And almost always, well, I think always, there are, you have to prove this, but basically given a supersymmetry and you wedge a gamma matrix of what we usually call making sandwiches over the epsilon bar with the epsilon with some gamma matrix in it, the first sandwich with one gamma matrix gives you a vector. And that vector is always a killing vector. I've seen proofs of this theorem in many, many contexts, but what you should always expect is no matter what, if you've got some supersymmetry, you should get a killing vector. Now, there's a whole slew of things you can do. You don't just have to make this sandwich, you can make many, many more sandwiches. You can put more gamma matrices in there and skew symmetrize and so on. And you get all sorts of interesting preferred tensors. And this is sort of where the whole generalized geometry story gets into it, looking at what the differential equations satisfied by sandwiches. All I care about here is the simplest sandwich that makes a killing vector. Now there's another obvious thing to do, which is we're going to use the killing direction as a coordinate. But one of the other things that we're going to, other issues is it time-like or null? This is a killing vector now, time-like or null. In this particular case, it's actually going to be null. But in general, it depends on the theory. In 5 dimensions, the killing vector for these black holes is time-like. In 11 dimensions, there is a possibility of time-like or null. So it depends on the theory you've got, and it depends on the supersymmetry projectors you're using. But in this particular instance, we're going to use the killing vector that must be there to make a coordinate u, and it will be, in fact, null. So there's a preferred null time coordinate. And that makes perfect sense holographically, because what it means is you've got all these left-moving modes, but the right-moving sector is remaining in its ground state. And this is really the time translation in the right-moving direction. That's why it's a null coordinate. So I think somebody was about to say something.
No, yeah, I just want to say in 5 dimensions, you can also have a null.
Oh, yes, you're right. Sorry, in magnetic configurations, yes. Yes, sorry, I take it back. If you do M2 branes in 5 dimensions, in other words, you use the projectors of M2 branes, then it's time-like. Joseph's absolutely right. If you use M5 branes in 5 dimensions, then the projector makes it null. So it does really depend on theory as well as on the projectors. In fact,
there's an intuition about this. Essentially, if you look at GTT, so when you have M5 brane killing spinners, the M5 branes have a common direction. So you have time and you have a common direction which have the same warping. And therefore, you can do something null. On M2 branes, the M2 branes are just a point in the transverse space. And therefore, the M2 branes don't have any common direction. So you can only do time-like. And when you have D1, D5, they have a common direction here. So you can do null as well.
So here the intuition is, if you think holographically, it's kind of obvious, because what you're doing is you've got D1, D5s, and what you're trying to do is you're trying to put some left-moving momentum waves, but the right-moving sector must remain unexcited for the supersymmetry, which means time translation in the right-moving time direction, which means that null direction. It must be an invariance of the system. But there are probably ways in 6 dimensions you can look for things which have null killing symmetries, but particularly the first observation that you make in this game of looking at the supersymmetric geometry is you basically have a null killing vector. Okay, so what do you do then? Well, you write down, and so far, although this looks highly specialized, this is actually just a completely generic metric, because here's the null coordinate, du, and all you're doing now is saying, okay, there's going to be some coordinate that pairs with it, or some coordinate v, and then an arbitrary vector, which we'll talk about at great length, in the directions of S4. So all I've done is I've broken this manifold into a piece, which I'm just going to call a 4 manifold. The warp factor could be absorbed into this, but I'm going to leave it out the front. So there's a 4 manifold, and then there's another coordinate v. And then that v can mix only with du. There's no du squared term because it's going to be a null direction. So this is a completely generic 1 form that multiplies it, and it becomes completely generic because I've thrown this warp factor out the front of it. So think of this as a generic 1 form. Now this generic 1 form compare with another generic 1 form, which I'm going to call omega, possibly some amount of the same generic 1 form. So at this point, this metric is completely general. There's nothing special about it. It's just I've written it in a very, very useful form. And these functions are going to be part of our life for much of this discussion of superstrata. So generic 6-dimensional metric with U. And moreover, the other thing you should realize is everything here is allowed to depend on the V and also on the coordinates of the DS4, which we will call generically X. So basically, everything's independent of U, but can depend on all the other variables. Okay, now that's the M4 is of course embedded here. So what we're looking at is with a null U coordinate, typically to recover the original sort of coordinate system T and Y. This is U is the right moving guy, Y is equal to T. And maybe I got this the wrong way around. V is the left moving guy. But these are the relationships I'm going to use between the original T and Y coordinates a time, and then I'm also going to, excuse me, periodically identify the Y coordinate with some radius Ry. Sometimes it's interesting to look at the Ry that goes to infinity limit, but for me, this system will always be compactified on a circle, radius Y, Ry. Excuse me. Okay, now, unfortunately, in the literature, this is one of many things that's going to happen, is that the base geometry is traditionally called B. And so I've been calling it M4, but it's now going to be relabeled and called B. So I'm going to use both of them schizophrenically. But then there's going to be this metric H mu nu, which is at the moment going to be a generic metric on these coordinates X, with the coordinates X on the 4-dimensional base. Okay, so this so far just notation. But the first step in making this into a BPS geometry is we have to look at what's called, we sometimes call the 0th order of the BPS equations. We have to look at the conditions on the metric on B, this metric, and on this fibration vector beta. We're going to worry about the rest of it later. But for the moment, it's really all about the base geometry. And this part of the thing is the hardest and most hardest in some sense, because it's the only intrinsically non-linear part of the process. But by the time we get to Superstrata, we make the dumbest, stupidest choice there is, as we will see. Okay, so now some definitions. And these, you're about to get into all sorts of horrible definitions. Part of my job here is to tell you where the bodies are buried. So in this game, we want to separate out, the base dependence, which is normally called X, from the fiber dependence, which is called V. And so everything is going to be thought of as a function of X on the 4-dimensional space. And we're going to think particularly of forms on the 4-dimensional space. But whenever they have a leg in the V direction, we're going to write it explicitly. And in particular, we're going to invent this exterior derivative, which is only the exterior derivative on the 4-dimensional X coordinates. And I've already screwed up my notation. I'm using Roman letters rather than Greek letters, but okay, you're going to have to bear with me. So basically, we're going to think everything's going to ultimately devolve down to the geometry on this space B, and we're going to be very interested in particular forms on this space B, and then the fiber will be part of the ancillary structure we're going to stick on top of it. So far, we just defined an exterior derivative on the base only. Okay, now, there's a D that we will also need, which is sometimes written curly D or capital D, and it's the same exterior derivative, but with a sort of what we call a fiber covariant derivative. Actually, this really is a covariant derivative in the sense of, if you think in terms of Kaluza-Klein, the beta is the vector field you get from Kaluza-Klein, and then dV of phi would be the charge under the U1 fiber, so it's an eigenvalue. So this really is the covariant derivative in the Kaluza-Klein sense, but it's, for the moment, it's just a generalized differential on these manifolds. Okay, now, here is one of the most painful, horrible, and disgusting parts of this process. Gutowski, Martelli, and Real use a very peculiar definition of the Hodge dual in D dimensions. And this, out of necessity, has therefore infected most of the superstratum literature. The rational and sensible definition of duality in most of the rest of the universe, like Nakahara, and if you use various Mathematica codes, like these tensor dual codes and things like this, and Van Ransdonk code, the duality is defined this way. And the difference is simply where the indices on this epsilon. You reverse the order of them. This is the rational universe, and this is the universe of Gutowski, Martelli, and Real. I don't know where it comes from, but anyway. It only makes a very small difference if you are in odd dimensions, it doesn't matter because you've got to reorder these indices, and that's always then an even number of reorderings in odd dimensions. But if you're on even dimensions and you have an odd form that you're trying to dualize, it changes its sign. There are going to be many signs and factors of 2, but I just wanted to warn you, one of the very first bodies of buried is this weird definition of dual. And it's used in most of the superstratum literature. Okay, so go ahead, Joseph. So Joseph, go ahead.
Yes, I'm just wondering, this restricted on the previous page.
Yep.
Why do you call this a restricted superstratum, a restricted exterior derivative?
Because the normal exterior derivative would involve DdV.
Oh, I see, I see. So you treat it as a V, so you treat V as a label.
You treat it as a coordinate. If I write full D, I mean the full D, including dV wedge DdV. But
Okay.
this is the restricted covariant derivative differential,
Okay.
which acts only on the base.
Mm-hmm.
And so in here, this is only acting on the base, and so forth.
Mm-hmm. Good.
So the way, as you know, the way we're going to think about this is everything that's going to happen is on the base geometry, and then everything else is just going to be a derived quantity following from that base geometry. So all the magic is in B. And the word of warning is I'm going to use these conventions.
Nick,
okay.
can I just
go ahead?
Just wanted to, Hodge dual stuff. I know we talked about this a lot. For people who are wondering, for example, the supergravity book by Van Pruyen and Friedman, this uses also the same superstrata conventions. So
you're joking, really?
Yeah.
I picked up. Yeah. So who the hell is it? The Dutch. The Dutch are guilty of many things in this respect. You know, be warned. The Dutch, for example, use the Ricci tensor with the opposite sign to everybody else. They trace over the first and fourth index.
Well, that's a travesty.
Old school Dutch. That's a travesty. Yeah, well, okay. But I thought with Harvey, it was probably Cambridge inference that they used the funny duality, but okay. You know, obviously with Dan Friedman and, you're talking about Dan Friedman and Van Pruyen's book, right?
Yeah, that's right. Yeah, their supergravity book, yeah.
Yeah, okay, thank you. Okay, well, beware. There are many, many traps, but most, but not all of the superstratum literature use this funny convention, and we usually have some footnote somewhere saying we're using stupid conventions. Okay, but every time you try and write mathematical code for it, you have to do it in the other direction. Never mind, you understand what I'm getting at. Okay, so I promised that the base you should expect to be something like hyperkähler, but it's not exactly hyperkähler. It's called almost hyperkähler, but that is actually not very helpful because if you look up almost hyperkähler or quaternion hyperkähler or anything else like that in the mathematics literature, you find 0. So I'll explain more about that. So basically what we've got is we've got 3 complex structures, and they satisfy the quaternionic algebra. They square to -1, and they basically commute into each other. So they are anti-self-dual. They also satisfy a differential equation, which is the exterior, but remember, this is only on the base, is equal to the V derivative of beta wedge, the thing you first thought of. There's some kind of strange differential identity. And moreover, the vibration vector, the thing that turns up in the metric here, has to satisfy this equation. It has to be, remember, this is this funny covariant derivative. It's d twiddle plus beta dot wedge beta. So it's basically got to be self-dual with respect to this covariant derivative. So this defines what is called by Harvey Rial an almost hyperkähler structure. It is not, a hyperkähler structure would have this being 0. And then, the hyperkähler structure doesn't care about this, but this is the almost hyperkähler structure. But in fact, this condition, if you look at it if you take d twiddle on this side of the equation, you get 0, but you push it through this, and you'll find that essentially you get, I think, a differentiated form of this equation. So this is almost, but not quite, an integrability condition for this equation. That's almost hyperkähler. So what I want to note is that if you say the geometry is V independent, and basically that means the fibration and the metric on the base, then it reduces to this twiddle is equal to 0, because nothing depends on V. Moreover, beta dot is 0. So this just becomes the standard thing. So this means that the base is actually honest to God hyperkähler, and the vibration is actually that of a self-dual Yang-Mills theory, self-dual U1, I should say. So V-independent geometry makes life a lot easier. But in general, you have to, everything's V-dependent, so in general you have to solve this. And this is what is known as almost hyperkähler. And as I say, I spent some time searching through the mathematics literature, and essentially nothing is known about what these things are. They're something. In particular, there's an old, actually one of my favorite stories, an old Larry Niven story about how the devil decides to kill off all philosophers and scientists. And what he does is he produces a problem that's so tantalizingly interesting that they hear about it and then they start thinking about it and don't eat, don't sleep, and don't do everything and waste away and die. Well, this is one of those problems, I think. Because if you look at this a little bit more carefully, you see that this is actually self-dual Yang-Mills theory. Because what happens is, because you can decompose into modes of along the V fibration, and then basically when you decompose it into modes, this becomes the self-duality condition with respect to the structure group, which is actually the diffeomorphisms of the circle. So self-dual Yang-Mills, I thought, well, that could be good. You could spend your life looking at this. I could not solve this system. But anyway, Benioff and I and a few other people spent a chunk of time trying to figure out how this system works, but to no avail. It's tantalizing, but nothing is known, and I don't know anything more than I'm telling you. Okay, so that's the base geometry, and you can get to that without knowing anything about the tensor gauge fields. So that's what Gutowski, Martel, and Rial do. And I don't think I put a reference here, but the reference here for this part is you can now add an extra tensor gauge multiplet, which means anti-self-dual tensor gauge field plus some scalars. And essentially, this paper's McConmer and Cariglia and McConmer. They also add vector fields, but we're not going to do that. So the first thing you do is, remember, you've got a three-form field strength. So you do the obvious thing. You introduce electric potentials. And we call them electric potentials because this multiplies du dv. And then there's some other pieces. I've written the one forms that appear in the metric. But it's really, this is z to the minus 1 du dv. So this is the analog of the electric part. And then, because you now have an anti-self-dual tensor multiplet, that means that it gets together with the one of the gravity and makes an unconstrained tensor multiplet. And then the dilaton, you also have the dilaton, and it turns up and in the joule of this guy, and it has another electrostatic potential. And then there are the magnetic pieces. And you find that the magnetic pieces are constrained by supersymmetry in the following form. Notice I'm referring everything to the base geometry. Star 4 means the Hodge dual on the base. So this is where the whole signs of, this is an odd form, so the signs are already going to bite you here. But anyway, the supersymmetry tells you, first of all, that there's a constrained form for these magnetic pieces. And it's basically the dual of some derivatives of your corresponding potentials. Notice how 2 winds up in 1 and 1 winds up in 2. That's going to be a feature that comes out of this. It's because there's a symplectic form lurking in the background here. And then the fiber multiplies something else, which now this is, of course, the explicit one form of the fiber. So this is entirely on the base. This is entirely on the base, and these are 2 forms. So the data underlying this is that there are 2 functions, Z1 and Z2, which are basically determining the electric potentials. And then there are θ1 and θ2, which are the magnetic 2 forms on the base. So essentially what we're doing is we're taking the 3 forms, looking at how supersymmetry tells us they're constrained, and pulling out the essential data. And hardly surprisingly, the essential data involves some electric potentials and some magnetic fluxes. Okay, any questions at this point?
Nick, I just want, could you explain the unconstrained tensor? Like, could you explain that a little bit more?
So in n equals 0, you just have a gravity multiplet. And the gravity multiplet has a self-dual tensor gauge field, B mu. So G would have to be equal to star G.
Okay.
But when you add an anti-self-dual one tensor multiplet, you have one anti-self-dual tensor field, and together a self-dual and anti-self-dual can be viewed as a single unconstrained tensor field.
Oh, okay.
Self-dual, which means that the G and G star, and the dilaton turns up in general in these kinds of duality relations, basically are independent fields. Z1 and Z2 electrically. Sure. A priori, G1 and G2 would be independent of each other, but they're not. They're related to the other fields. And the only new arbitrary thing stuck in here is the piece which is a 2 form that multiplies the fiber.
Oh, okay, okay.
But at the moment, so what it means is, if in the n equals 1 theory, there would just be Z1 and there would be theta 1, and I think Z1 would be Z2 and theta 1 would be theta 2. I'm not sure of that, but it's something like that. But the point is, if n equals 1, we're going to need n is 2, so that's where we're going next.
Okay.
So if you go to n equals 2, there are now 3 tensor gauge fields, but there's going to be a duality relationship between them, which I can write down in a few minutes. But basically, it's exactly the same deal. You basically have electric potentials with exactly the same format, and the things are d of electric potentials. And then you have these magnetic pieces. I even got the halves right, with theta 1, theta 2, and theta 4. And for historical reasons, 3 is being dropped out of the lexicon. So we count 1, 2, 4 when we do superstrata. I think we like counting exponents and powers of 2 or something. But actually, the real reason why the label 3 is missing is because we first started doing this in 5 dimensions. And when we went up to 6 dimensions, the theta 3 and the Z3 became a Kaluza-Klein fields. And so lurking there, beta is really theta 3. Or d beta is theta 3. So for historical reasons, 3 disappeared because we went from 5 to 6 and 8 up theta 3 and its potential. We'll see what come back later. But anyway, there are now 3 tensor fields. And I don't want to go too much into the details of the duality of these things, but the important thing is that every time you add a tensor field, you add a electrostatic potential, or electric potential, I should say, and you add a magnetic flux. But all of these are functions on B. But remember, they're allowed to depend on V. Okay, now I put this in as a quick note. It's in there. If you want to express the duality of these forms in a nice way, there are all sorts of horrible factors of 2, and in particular, you've got to go to the standard superstratum literature and divide this 4th guy by √2. And then what happens is you introduce a sort of Lorentz matrix. This is SO21 matrix on the defined on the indices 1, 2, and 4 because it's 1, 1, 0, 0, and then there's a -1 eigenvalue. And then these tensor gauge fields can be written nicely in terms of this eta and so forth. And there's a twisted duality condition. And the twisted duality condition, there's a plus or minus that depends on your duality conventions. But I think we choose minus because we want anti-self duality. But anyway, the end of the story is that these things satisfy a duality condition where this thing is folded in with a scalar matrix, which is made out of this ratio of Z's and P's. So I don't want to go there in great detail. We're not going to need this at the moment because we're not going to solve equations of motion. We're going to solve BPS equations. But this mess here, let me step back a few slides, generalizes this statement here that G and star G are related to one another by this kind of flipping of Z1 and Z2. So at the end of the day, there is a duality condition on these tensor gauge fields, which cuts the degrees of freedom in half from what seems to be stuck here. Okay. Right. So now we're going to start looking at the BPS conditions on these tensor gauge fields and on all this, and on the background. So first and foremost, there is the dilaton axion. Now this is just reparameterizing the scalars. Remember, we got these electric potentials Z1, Z2, and Z4. Z4 over Z1, this new guy, the 3rd guy that we've added, is giving the axion, and the dilaton is given by this. And if you put Z4 to 0, you're going to go back to n is 1, and you're going to wind up with this being Z1 over Z2, which is the standard sort of dilatonic expression, and there's no axion. But this function P, remember, is the function P that turns up in the metric. So what we're finding here in this relationship is that the electrostatic potentials are related to the warp factor in the metric. And if you think what happens asymptotically, if you want to look for the ADM mass, you look at the coefficient of dt squared at infinity, and you do the asymptotic expansion of the metric for large R. And that tells you you've got to do an asymptotic expansion of this guy. And what that does is that this link here is what actually, in great detail, enforces the statement that the mass of this thing is the sum of the electric charges, if you do it all correctly and properly. But here's the first non-trivial constraint, which is that the electrostatic charges are locked to the warp, one of the warp factors in the metric. And these are, I put this in completeness. This is just saying how you lift back to the 2B theory, but they're the dilaton and axion. Another way of putting it is the dilaton and axion turn up in the rest of the 10-dimensional ansatz in terms of the size of tori and things like that. Oh no, not in 2B. They're just the dilaton and axion. Take it back. Okay, so now we're going to start looking at the conditions on the fields. So remember, let me back it up a second. Remember the data that we're now focusing on. Remember, we're looking at only equations on B. The goal is to get everything down to B. And so we have 3 potentials and we got 3 thetas, all on B, and we want to know what they look like. Okay, now there's one last gasp of this horrific, almost hyperkähler structure. If you look at this beast, basically you take one of the hyperkähler structures, J1 say, contract it with the derivative, V derivative of J2, and then take the full trace of that and then multiply by J3, and then you sum over the epsilon symbol and multiply by root P. Now, remember I said the J is anti-self dual, so there's this ghastly anti-self dual 2 form made in this way. And the whole point about this is to say the thetas that you're going to throw on aren't quite self-dual. They are almost self-dual, but if there's a uniform piece you subtract off. Theta 1, you subtract off a certain amount of anti-self-dual here. Theta 4, you have a certain amount of anti-self-dual, a certain amount of the anti-self-dual guy. And then the result is self-dual. So it's self-dual up to this ghastly thing psi. And believe me, we're going to get rid of psi as soon as we possibly can. But in general, these fields are not quite self-dual. There's an anomalous failure of self-duality, and it comes from this term. But if things are V independent, this is gone. Okay, now here's the infamous first layer of the BPS equations. So basically what you have to do is you have to start solving differential equations. They are always first order in this sort of game. And basically that's what you have to solve to construct the BPS conditions. So the first thing is, essentially what happens is you get this covariant derivative D of the 2 forms. This is a 3 form, and here's its, oops, I think I may have that look, oh no, this is right. I think I'm a little bit worried about this, but okay. I think that's right, okay. And then it must be related to the dual of its corresponding function. So 1 is related to 2, 2 is related to 1, and 4 is related to 4. That's the structure of this eta matrix I was talking about before. And similarly, if you take d star of this, you get theta wedge d beta. Now you can actually, this is the derivative of an integrability condition for this equation. But the most important thing is to notice that this system up here is, you're trying to solve for theta 1 and z2, and theta 2 and z1, and theta 4 and z4. And this is a linear homogeneous constraint on these things. Homogeneous. This is also linear and homogeneous for each of these pairs. Theta 1 is paired with z2, theta 2 is paired with z1, and theta 4 with z4. So the most important takeaway message here is, yes, these are ghastly equations, but they're linear, and it's a homogeneous system. So basically, it's doable. And remember also, these are differential equations on the base of the manifold. So we're dealing with essentially a 4-dimensional Riemannian manifold. It's got this funny, almost hyperkähler structure, but this is a linear system of equations to be solved on that background. Okay, so now, yeah, little comment. It's the linearity of the BPS system that actually makes the superstrata manageable. And this is the sort of breakthrough that we made in 2011 with Joseph Masaki and maybe, I can't remember who was on the paper, but basically we made this breakthrough where we realized Gutowski, Martelli, and Real and Corriglia and McConnell had done a huge amount of heavy lifting analyzing the BPS equations, but by using these this interesting ansatz that we evolved for the tensor gauge fields, we actually managed to make that system linear. So that was a sort of huge breakthrough for making these kind of solutions.
Can I make a comment?
Yeah, go ahead.
typically British. So this is, people solve all these equations and, they went through the system and, they just went like a bulldozer and, essentially, when you go like a bulldozer, there's like this tradition of like, going like a bulldozer and solving everything and finding all the equations and so on and so forth. And, basically the trick is sometimes, don't go like a bulldozer and look a bit around and maybe you can find something interesting.
So the thing that gave us the clue is we'd also done this, and Joseph and I had also found linearity in 5 dimensions. So I remember it was an Aspen. I was actually trying to disentangle this. So I remember banging on Joseph's apartment door about 9 o'clock in the morning some Sunday, waking him up and telling him, it's linear in 6. So the point is, this was, it's a technical point, but it's a huge breakthrough for reasons that I'll say more about in a minute. Okay. So now, the last layer of the BPS equations, I've talked about beta, but what we haven't talked about is omega and F. So this is what determines, or this is sometimes called the angular momentum vector. It encodes all the information about the angular momentum of the solution. And F is what's going to carry ultimately the momentum charge. But we haven't determined those yet. But again, once again, you can tease out from this horrible system in GMR and its generalizations that we've made, a linear system. But first, before you do that, you have to realize that there's a coordinate redefinition. You can make a redefinition of U. This does not change the fact that DDU is killing, but you can always redefine U by any function of the other variables, and therefore this kicks something that the DDV part can shift F, and the DDX part can shift omega. And so there's a gauge transformation that inherits from this possibility of being redefined. So really what you should expect is not an equation for F and omega, but for the gauge invariant quantity, which is defined like this. So this looks like hell, but in fact, you just have to realize that it's the thing that's invariant under this gauge transformation. So the second layer of the equation is something only its mother could love, I think, but let me explain what it is. It's basically the divergence of this one form, and then beta dot contracted into the components of the same one form. There's this ghastly thing, psi plus d omega, and here's the right-hand side. And so I'm going to sort of unpack it a little bit. So what's going on here is that you have a v derivative of your base metric, and then you can trace it out. And then you can take the v derivative of that, and this is the warp factor up here. H is the metric here. So this pile of crap is all to do with how the metric H depends on v. And similarly, the warp factor here, P depends on V. But then there are all these other pieces which have to do with the V dependence of the electrostatic potentials, and also here's how the magnetic things contribute. And notice I've written them for the sake of being nice in terms of their self-dual pieces. And then there's a second equation. And if you count up the number of equations, you have exactly four equations, because why? This is a self-dual equation, so it's a 2-form, but it's self-dual, so really a self-dual 2-form only has 3 components, and in particular that means this is 3 equations, and this is 1 equation because it's the divergence of something. So it's 4 equations. You have 5 unknowns, omega and F. Omega's got 4 components. There's a 5th one here, but there's a gauge invariance. So you have exactly what you need to solve for omega and F. And the other thing to notice is it's linear. So on the left-hand side is only, the omegas and Fs only turn up on the left-hand side, and they're all linear in omega and F, omega and F. So once again, it's a linear system. But now it's not homogeneous anymore. You've got these god-awful sources on both sides. So it's a linear system, and the way it works is that you pick the geometry. That's the only nonlinear part. Having chosen the geometry, you then find these solutions to the tensor gauge fields and fluxes, but then they appear quadratically on the right-hand side. And schematically, you sort of expect this, because the equations you're really solving, at least in 5 dimensions, are things like d star f is f wedge f and so forth. And what's actually happening here is you're getting the sort of first order d star f's on the left-hand side. And this is the sort of residue of the f wedge f. But what saves you is that d star f is f wedge f is a horribly nonlinear equation. But what saves you is that there's this sort of upper triangular structure to this thing, where in fact the lowest layer, the first layer is linear and homogeneous. The second layer is linear on the things you want to know, and then quadratic in sources constructed from things you've already solved, which is this is the geometry and these are the fluxes. This is the that we want to solve for this, and this is the geometry and fluxes. And there's a sort of intuitive picture with this lot here too. This is, remember, an electrostatic potential, and this is a magnetic field. And so within these kinds of systems, you get the angular momentum from an interaction of an electric field and a magnetic field. And so this is the sort of basically E cross B term that you would get precisely that generates the angular momentum of these solutions, and also the momentum charge of these solutions. Okay, so the whole point of this is the right-hand sides are inhomogeneous sources that are based on things you already know. Okay, so the bottom line, once you've chosen your almost hyperkähler geometry and vibration, the entire BPS system equations is linear. And the first layer, you have some kind of strange self-duality condition. You have these first-order equations. For the fluxes, they're homogeneous. And then the second layer is you take all that you know from this lot, construct the source, and now you have another set of linear equations to solve. And to sound preachy, the linearity is of immense practical importance because you can actually solve it in the right context. But the other thing also intellectually is important to realize is that you can apply the superposition principle to solutions. So once you have one, and the other beautiful thing which we use hugely in Superstrata is if you find a linearized solution, you've got the whole solution. Because in other words, if you linearize the fluxes or linearize the, if you linearize the fluxes, once you've got the linearized fluxes, since these equations are linear, you know what they are at arbitrary order. That's number one very important, useful tool. Secondly, there are tricks for making single linearized fluxes, but now, because it's a linear system, you can superpose them and make lots and lots of much more complicated solutions. The only price you have to pay is, of course, that this equation, while linear, if you start linearizing the solution, you start getting very complicated quadratic forms in the fluxes. So therefore, you have to solve a new inhomogeneous system. But in terms of the intellectual territory, the linearity is also very, very important because it means that the solutions in the phase space is comprehensible. I originally sort of got into this story about 15 years ago because my goal was to show that it was impossible to do fuzzballs and anything remotely like Superstrata in the 3-charge case, because my goal was to prove it was nonlinear, and therefore you couldn't find any sensible way of describing the phase space of solutions. Here, it turns out, even in 6 dimensions, the system is linear. It looks terrible, but we're going to start simplifying the hell out of it. Any questions or comments? Okay, so the first simplification, which is what we do. We're going to avoid the base space, the base space and the vibration having any V dependence. We're going to kill it off. I have no idea how to find, there are examples. I think there's that, was it Saxena, Justo, and something other. Joseph, help me, who's the third author on that?
I think just Saxena and Justo.
Saxena and Justo, they have a solution where they do some they do some coordinate transformations to turn something that doesn't depend on V into something that does depend on V. But the number of solutions.
The flat space back.
Yeah. There are some non-trivial solutions where you have V dependence, but they look like hell, and I've never seen a use for them. But there must be. Wrenches my gut to do this because I'm sure there's a lot of interesting microstate structure in V-dependent vibrations, but I can't do it. Okay. So the first thing is we're now in hyperkähler territory. And in particular, this beta field is self-dual. There are 3 complex structures, and that horrible thing that I call psi is gone. So it's never going to give us any. By the way, this is what's usually called θ3. This is the Kaluza-Klein magnetic component, and F is actually Z3. But basically, now the first layer equation begins to look more manageable. The first layer is, on the base, you find self-dual 2 forms. Then you take those self-dual 2 forms and you wedge them with betas, and then you solve this albeit covariantized, Laplacian on each of the electrostatic potentials. So what you're getting here is, this is really Chern-Simons in action, because what's this is an electrostatic potential. This is the Laplacian, and the Laplacian on this electrostatic potential is sourced by the wedge of two different magnetic fields. So basically you're getting, these solutions are deriving their charges from the magnetic fluxes. Okay, so the first layer is now much, much more tractable once you've got rid of the V dependence. And then the second layer is not so bad either. The second layer is now this angular momentum vector, it's d plus star d of omega, plus this f d beta is given by these E cross B terms, electrostatic potentials, magnetic fluxes for all of these fields. And this, morally speaking, is just the divergence of the, this is the Laplacian on F, is sourced now by the V derivatives of Z1, Z2, and so forth in this rather controlled way. So this is actually what we tend to try and solve, or want to solve. And notice what we're doing is we're requiring that the geometry and the vibration are V independent, but everybody else, in particular the magnetic fluxes, are V dependent and allowed dependent V. And this is essential because the goal at the end of the day is we want to describe left moving momentum waves on the D1, D5 system. And the left moving momentum waves are a traveling wave that depends on V. So it's essential to allow the fluxes and the charges to actually have this V dependence. Otherwise, you're not going to get what we set out to get. Okay. So I just want to revisit two things sort of as we go by. Going back to the uplift. So I won't do this again, but I want to remind you that really we are working in a 2B solution. We are getting the full 2B supergravity solution. And now we have these Zs and Thetas. And I wanted to sort of show you where all the bodies are buried in terms of the full 10-dimensional geometry. This is the sort of dilatonish factor, but it's Z1 over Z2, which controls the 4 torus volume. There is a new warp factor out the front of this, which is made out of this quantity. Notice for Z4 is 0, this is not there, but for Z4 non-zero, it's there. Here's the 6-dimensional metric, dilaton, axion. Now, for the B field, you see that this is the B field, the Z4 really is the electric charge of the Kalb-Ramond field. And similarly, Z2 is the electric charge of the C2 field. And so therefore this represents the sort of D1 string, D1 branes. And C4 is the electric, where's it gone? Yes, the electric charge of the, essentially of the corresponding D5 branes. And then we've thrown in for good luck all the other, the C6, which is the dual of the C0 and so forth. Now, there are these quantities that I haven't defined, A1, gamma 2. Remember, these are gauge fields. And so therefore there are gauge transformations. So there's going to be some ambiguities. And so let me explain what they are. So if you want to figure out what, say, A4 and delta 2 are, you take theta 4 and you write it. Sorry, I've changed my font. This is still the same covariant D. So A4 is a potential for this, and it's defined up to some V derivative of something. So basically, there's a gauge dependence folded into this B field. If I take D of B, I can write it out much more generally without these A's and so forth. But the whole point is that once if you want to build the B field, you have to fix some gauges. And so the gauge fixing is inherent in how you pick this potential here. And similarly for the A2, sits inside, A1 sits inside C2 and gamma 2. And similarly, where's it gone? The other A, whatever, there's another A sitting here. So yeah, A2 and gamma 1. So basically, you have to pick gauges. And then there's a last one, which is buried here called X3. And X3 comes from another one of these ways where you take the field, you take something and you write it in terms of some differential of A. So anyway, the whole point is you could write all of this, if you wrote the field strengths down, you could write all of this in a gauge non-invariant way, but I wanted to write it in terms of gauge potential because it's easier. There's another very important take-home message here. So Z2 is controlling the D1 brane, and Z4 is Z1 is controlling, where has it gone? Have I got this the wrong way around? This is the, sorry, this is D1. Oh yeah, excuse me. Z4 shouldn't be, I'm getting confused about this. I want to put alternate for Z4. I'm sorry, this is the D5 brane. Yeah, sorry, I take it back. This is I think it was D5 brane. Yeah, so this is electric status. So Z1 is controlling the D5 brane charge. I think I've got that the right way around. Anyway, the end result of this story is that Z4, which is the sort of late comer to the piece, we didn't have Z4 in the picture when we first started doing 6-dimensional solutions. But adding Z4 turns out to be essential, and it's going to be a really critical part of the story. But when you add Z4, you are adding the Carl-Bramond field, and you're adding it in a way where you add Z4 as electric potential. Moreover, you're adding a magnetic piece, because Z4 is related to, also contains a θ4, which contains this A4. And the magnetic piece and the electric piece are tied together in a very specific way. So it turns out you can't make smooth solutions without including the Carl-Bramond field. And so Z4 turns up here and also turns up in the axial. So if you kill off Z4, you kill off the axial and you kill off the Carl-Bramond field, because Z4 goes away, then θ4 goes away, and then this is 0. So Z4 injects into this the axion and the Carl-Bramond field. And without it, you're just dealing with D1, D5 system, but possibly with traveling waves. Okay, so sort of closing a loop. This is a route not taken, but I want to just tie it back to my old lectures and tie it back to things we did 10, 12 years ago. Suppose that everything is independent, everything, not just the geometry, but all the fluxes and all the potentials and so forth are independent of the V-circle. Then what happens is the BPS equations I've just written down, you get self-dual. Let me put it back. Where are they? There they are. So if you make everything independent of V, this term drops away, this D becomes an ordinary D, so you get d theta is 0. Basically, this becomes an ordinary divergence and so forth. Everything drops away out of the system, and you wind up with basically completely standard self-dual Maxwell fields on the base, magnetic, and the magnetic components are magnetic self-dual, and then the electric potentials are simply read off from this Laplacian on the being equal to F wedge F, and then the angular momentum is exactly given by this. So these equations we've studied really well, we know how to solve them, although there are still some surprises in them, as we discovered when we did the MSW string. Okay, so this is the 5-dimensional system, and it's kind of obvious what you do to get there. You basically, as I say, you make everything independent of V, and you wind up with, this is called K, and K is omega, and this is Zi theta I. This is θ3, and this is Z3, or minus Z3. And so this is the historical reason why Z3 and θ3 disappeared. And θ3 I've actually written as being d beta. So this is the 5-dimensional BPS equations. We're not going to solve them because, as I said, we want to make traveling momentum waves, and that means we must have V dependence. Now, in the notes, I've also put another way. There's a second way to go down to 5 dimensions, which involves a slightly different set of identifications, and both are useful to know, and they're not exactly the same. They redefine various coordinates and various fluxes, and I put them in the notes, but it's useful to know both of them. Okay, so as I say, the V dependence is essential to describing the left-moving momentum waves. Oops, my transition seems to have gone wrong. Okay, so what I want to do is start setting up, since I've timed this about right, I wanted to have an hour of material. So basically, Superstrata, what are we going to do? Yeah, go ahead.
Can I ask a question?
Oh, please, absolutely, yes.
Yeah, so we have only been solving supersymmetry equations. We have not looked at a single equation of motion at this stage.
Okay, in here there are, I think, so there's a question buried in this discussion is the fact that when is it sufficient to solve the BPS equations to produce a solution to the equations of motion? So in other words, if I solve the BPS equations, have I solved all the equations of motion automatically? And the answer is no. Although in some cases, yes, but generically, no. So let me give you the simplest example of this. Is suppose I put down a single charge brane, or distribution of branes. And I say, okay, my distribution of branes has some electrostatic potential, which I'll call phi. And now I've got some warp factor in the metric, which scales the space-time or in some way, and I'll call that h. The BPS equations tell you that h is phi. The BPS equations do not tell you that h has to be harmonic. So sometimes, in very simple circumstances, solving the BPS equations gives you constraints between fields, but doesn't give you all the differential equations you have to solve. Now, there are theorems about this. Jerome and his group in Imperial have proved a lot of theorems about this sort of thing. One of the theorems is that in, I think it's 11-dimensional supergravity, you need to take the BPS equations, and all you need is one of the Einstein equations. I think it's the plus component of the Einstein equation or something. So I think the same is true in the GMR story, Gutovsky, Martelli, and Real. One equation of motion has been injected into this to give you the full system. So it's a little bit sneaky because the equation of motion is the self-duality of a three-form field. So it looks first order, it looks like a BPS condition, but it actually is an equation of motion. So some of the self-duality constraints are required by supersymmetry, but I think not all of them. So we have injected the equation of motion into this. Now that's
actually,
one.
Motion is in the when you look at the star d z.
Yes.
But that's not the self-duality. This is just
yeah. This is an equation of motion. You get a version of it from the BPS, if I remember rightly. I think you get the pre-potential of this. So what you get is you do need to add the equation of motion, but you do get constraints that involve remove a d from this. In other words, this is d of star d of z. You can remove a d from this, and you get a potential wedge of theta.
Yes, that one we get from supersymmetry.
That comes from supersymmetry, but you don't get the whole thing, because you get some sums and differences of these, and you need the last equation supersymmetry you need. I think you get sums and differences of those pre-potential versions of this equation, if I remember rightly. So that's half of Bogdan's question. The other half of the question is, have we just gone and solved the equations of motion outright? The answer is we've done this in some examples in 5 dimensions. They're called the almost BPS solutions. So what we do is we use pieces of the BPS equations to constrain the solution, but we don't impose the full BPS set of conditions, but then we have to go and check the equations of motion and check that they work. So for example, the cheapest way of doing this is, remember I kept saying in this situation, since everything's V-dependent, the base has to be hyperkähler. Well, now you can say, suppose I make it Ricci flat, but not hyperkähler, but I impose these conditions. It's not supersymmetric, but it does solve the equations of motion. So in some cases, we've looked at more general classes. The whole almost BPS program, which is something we were doing, I don't know, 10 years ago, we found a whole bunch of things that were almost BPS. They're not how to put it, these solutions are kind of artificial because they tend to be extremal. They're not.
There's one example actually where you just use as a Ricci flat manifold the Euclidean version of the Schwarzschild black hole.
Yep.
And then we get something which you call the running bolt, which is actually not extremal.
Oh, sorry, you're right, because it's got a mass parameter.
There's some other problems, it's hard to define spins on it and so on and so forth, but
it's a perfectly good solution. Yeah. And so we have moved a little bit beyond BPS equations into more general things. But if you ask the question, have we gone out cold and tried to solve the equations of motion? The answer is no, except maybe I'll get to this if I get in this course. Well, there's this stuff that I did with Robert and Daniel where we reduced down to 3 dimensions. And then it becomes more practical just to try and start looking at equations of motion. And in fact, we looked at that consistent truncation, and what we proved was the equations of motion work. We didn't prove yet that the supersymmetry is as we said it is. So the honest answer to your question, Bogdan, is very little has been done with equations of motion that go beyond the sort of BPS setting. There's the whole almost BPS story is the most non-trivial thing we know. Did I answer your question?
Yes, you answered way more of it. My question was basically, do we know how many of the equations of motion are satisfied by solving the BPS equation?
Oh, okay. Then the answer is these equations solve them because I've carefully and sneakily snuck in the things I need to solve the equations of motion.
Yeah, and the Maxwell equations are satisfied, I presume.
Yes, that follows. So these theorems, how do they work? So when you write down the BPS conditions, so one of the things you write down, well, maybe I can flip. Let me just share, new share. Maybe I can do this. New share. Do I have? Let me try this and see if this works. Share. I've got the whiteboard. See if I can. Oh, this looks like crap. Where's the Zoom whiteboard? No. Okay. Let me just start up a different app.
I mean, we do see a white screen. So
no, my problem is I don't see it. So I'm going
Oh, you don't see,
I've got an app here which I'm going to use. Where's it gone? White? Well, there it is. Sketchbook. That's what I want. There we go. That'll do. So when you start solving delta psi mu is equal to 0. This typically involves grad mu of epsilon plus perhaps some f Maxwell fields slashed with gamma matrices epsilon is equal to 0. You start solving that equation of motion. So when you look at the integrability condition for this equation, what you're supposed to do is you're supposed to look at the commutator of two such covariant derivatives. And the commutator of two covariant derivatives on epsilon is basically something like r mu nu rho sigma gamma rho gamma sigma sigma on epsilon as a quarter, I guess, but not going to matter on that side. But now you use this equation and you substitute in here for grad epsilon and keep substituting all the grad epsilons away. And what do you get on this side? You start getting things that involve derivatives and f's. And so what actually happens is, and then you also find some pieces which are f squareds. Okay? Follow schematically what I'm doing?
Yes.
So if you solve this equation, you must necessarily solve this equation. And so, for example, if you take the gamma trace on this, then you can show very easily, a trivial exercise, that this is r rho mu gamma rho epsilon. There's the beginnings of the Einstein equation. In fact, it's exactly the Einstein equation if you take the gamma trace on this. So you get an Einstein equation. And then on this side, when you take the gamma trace, you start getting f squareds, and then that turns to the energy momentum tensor. So if you solve this equation, you necessarily solve this Einstein equation, except for one thing. You've got all this crap, these derivatives acting on f. But those derivatives acting on f actually can be assembled into the equations of motion for f. So the short answer is that where you prove these theorems about solving supersymmetry is you look at this equation for openers, you look at its integrability condition, and you tease out of it the Einstein equations and the Maxwell equations. And so basically, the question is, does it give you everything? And the sort of theorems that you can prove are that if you satisfy all the Maxwell equations, you get rid of this, you get almost all of the Einstein equations except for one, which is the point is this is somehow degenerate with the gamma matrix in it. So basically, and conversely, if you solve all the Einstein equations, then you get the Maxwell equations and so forth. So the short answer is you usually only have to throw in one of the components of the equation of motion, and you've solved everything once you've solved the BPS equations.
Okay.
And there's a very simple example of it that I do in my in the previous lecture, which was my old lecture notes from last year, where I do go through and I show exactly the statement I made at the beginning. If you do this calculation for the simplest, stupidest charged black hole, what you discover is the warp factor in the metric has to be locked onto the electrostatic potential. But you only discover that electrostatic potential is harmonic if you actually solve the equation of motion. And so, since there are no magnetic fluxes, it's this equation, del squared z is 0, is an equation of motion. So the honest answer to your question is, basically, if you solve the BPS equations in a complicated enough system, you've solved all the equations of motion. This is almost complicated enough. You just have to throw in one equation of motion, and it's already in there. So I've injected it. Okay, so my sequencing on that page has gone wrong. So superstrata. So the first thing you do is you want no V dependence. What's this? Yeah, sorry. The first thing I'm going to start looking at is I'm going to look at the D1, D5 P black hole. That's what I'm going to do. Well, maybe I'll just finish on that note. And so in the black hole, we have no V dependence at all, and we've got no magnetic fluxes. So the exercise of the superstrata is to take that black hole and add bells and whistles, add fluxes, add Kaluza-Klein monopole moments. And the goal is to turn and choose a nice hyperkähler geometry and vibration, and then turn it into something which is a microstate geometry that corresponds to the microstates of this black hole. That's what we're trying to do. And so it's worth just looking at what happens at the sort of supertube to start with. And that's what I'm going to just finish on. So we're going to take a completely trivial vibration. So that means we're going to kill off all of these terms. And we're going to make sure that, oh, that's right, excuse me. Sorry, I did type this late last night. Okay, so we're going to take a trivial vibration and we're going to kill off all the magnetic fields. We're interested in the black hole. What's the black hole? It's got no dependence at all. It's got no magnetic fluxes, and we're going to just kill off all that stuff. And so, and then all of these things will disappear as well. And what you wind up with is, again, you kill off all of this stuff in these equations. And essentially, at the end of the day, what you have to do from the BPS equations is find the harmonic solutions. And so essentially, all of this devolves to the most trivial thing you could possibly imagine if you trivialize everything. And if you make it non-rotating, you even kill off omega. And if you go to spherical polar coordinates, this is the basic D1, D5 black hole. Essentially, you write down as the Zs, you put constants in them to make them have nice asymptotics, and I'll mention that in a minute. You throw in harmonic sources. Z4 you throw away. We don't need Kalb-Ramond fields or anything like that turned on. We've got no magnetic fluxes. We have momentum charge, and basically in the trivial vibration, no angular momentum. These are the three black hole charges. If you look at large rho in the solution, you find it's asymptotically flat. That's because I picked ones in these harmonic functions. And if you look at small rho, basically you wind up with this sort of classic ADS2 times S1 times S3. So this is the D1, D5P black hole. And essentially, the horizon in this situation is going to be at rho equals 0. We're not interested in rho less than, it's actually rho squared less than 0 is inside the horizon, but rho 0 is not the singularity. It might look like that, but it's the horizon of this beast, and we're only going to be interested in the exterior region. So our starting point next time is going to be this, or actually starting with just the two-charged black hole. And what I want to do is go through and start talking about adding Kaluza-Klein monopoles and making that smooth. But essentially, in the superstratum, you do the stupidest, simplest thing. Let me get rid of this. Basically, you choose, even in superstrata, you choose a hyperkähler geometry and vibration. The hyperkähler geometry we choose is flat R4. And we're going to take the same round Kaluza-Klein monopole moment of the supertube. So here's the thing that sort of also hurts in a sense. We know we can build superstrata with arbitrary hyperkähler geometries. But to make the superstrata that is dual to the D1, D5P black hole, the ones that we can build, the choice of the hyperkähler manifold is simply flat R4. Now, what that means is that topologically, we're going to make something which only has one bubble. It only has this sort of big fat S3 in the geometry in the core. That's one bubble, one non-trivial topological cycle. If you have more general classes of hyperkähler geometry, then you can have multiple bubbles. And in principle, you can put momentum waves on each and every one of those bubbles. We do not know how to do it. It's an unsolved problem. Moreover, the first thing that also is an unsolved problem is basically taking something a little bit more general, epsilon more general, make that Taub nut. Do the same construction. We don't know how to do that even. So the only thing we know at the moment about how to add momentum waves to it is precisely when we take the base to be flat R4. It would be really nice to be able to do something much more general than that, general hyperkähler geometries. Even Taub nut is unknown. And it's because the flat R4, you've got to solve these BPS equations that I keep putting up here. You've got to solve these equations. And it all depends on how nice or nasty the base is. And if the base is R4 and it's written the appropriate coordinates, all these wave equations become separable, as we'll discuss next time. But essentially, getting beyond flat R4 is actually a fairly high priority. The other reason why we do this flat R4 thing is essentially because we don't know the holographic dual of generic hypercalar geometries. So one of the huge guides in constructing the superstratum solutions is we know precisely the holographic dual states we're constructing, and that has only been really done at least non-perturbatively for flat R4. Our friends who do the sort of ADS CFT calculations of this know the linear order perturbations to the background metrics that we have to do in order to get other classes of states, but we don't know how to integrate those linear perturbations up to get the full geometry. So this extension beyond flat R4 is a high priority, but we don't know how to do it yet. We only have linear data about how to perturb the gravity field. And I'm going to stop there, but I'm happy to field questions for the next, whatever, 20 minutes, half an hour, whatever people want to do. But I will start next time by basically starting with the black hole, then going to Klutz-Stein monopoles, and then talking about fluxes in those backgrounds and try to put it all together into making a first example of a supertube. First example of a superstratum. Probably the most important one that's easily studied. But that's the goal for next time. Questions, guys? Comments?
I have a question, Nick.
Sure.
How did we go from almost hypercalar to calar? Or could you explain a little bit more?
Let me back it up. So, okay, so almost hypercalar is this amazing thing that was discovered really by Gutowski, Martelli, and Real. So if you say, I just want to solve the BPS equations and I want to understand the background geometry, then you find that base manifold must have two forms defined like this, which satisfy this quaternionic algebra. J1 squared is -1, J1 times J2 is J3, and so forth. So this is the hypercalar means there are three complex structures, and they satisfy this quaternionic algebra. What is a complex structure? A complex structure says that on the tangent space you have a well-defined notion of multiplication by I. You can rotate. There's a conjugate variable which is the real, gives you a notion of real and imaginary parts. Hypercalar means you have an action of the quaternions I, J, and K, usually called J1, J2, and J3, and they have to satisfy the quaternionic algebra. And on a hypercalar manifold, the tangent bundle has an action of the three quaternions I, J, and K. But then there is the condition that this complex structure is integrable, and that I haven't written down. But it says that if I take an infinitesimal displacement of the geometry, I can't screw up the notion of multiplying by I. A holomorphic differential, if under a perturbation, has to remain a holomorphic differential. It can't start mixing with Z, and so forth. So that's called an integrable complex structure. And I don't know whether Gutowski, Martelli, and Real address the integrable complex structure. But if you have a calar structure, if D of the complex structure is 0, then it's automatically integrable. So a calar manifold has this and this being, this being 0. That's hypercalar, or calar if you only got one of them. And then integrability is contained in this equation.
I see.
Now, almost hypercalar involves this strange condition that the derivative of J, the exterior derivative of J on the base is not 0, but it's beta wedge, the thing you first thought of, V derivative.
I see.
Oh, this is completely unknown mathematical territory as far as I can tell, but that's what you get out of solving the BPS equations. So in Superstrata, and out of desperation, because we don't know how to do anything else, we just simply say, okay, the base manifold, this metric DS4 squared, we're not going to let it depend on V. And we're not going to let the complex structure depend on V. We're not going to let beta depend on V. And then you get down into the more familiar territory that we know and love, which is hypercalar manifolds with self-dual magnetic fields on them. That we understand how to solve. This is totally unknown territory. And this particular differential equation, this sort of Yang-Mills theory for diff S1, no idea how to solve it. And there's a bit of a blind I'm throwing you here. I'm saying, oh, this looks like the self-dual. When I first saw this, I thought, oh, maybe I can use the ADHM construction because this is self-dual Yang-Mills for diff S1. The answer is no, this is bullshit, because the whole point is that the existence of instantons requires a non-trivial third homotopic group. There has to be a pi 3 of the relevant group, and any non-abelian group has a non-trivial pi 3. It's the SU2 embedding. So the whole construction of instantons is all about that SU2 that sits inside the group. Well, the problem is that diff S1, pi 3 is trivial. Every sector is a deformation retract of the circle, so it's kind of, so in other words, there's no topology in diff S1 that can make interesting instantons.
I see.
But still, there should be, this is the self-dual Yang-Mills theory for diff S1, whatever the hell that is. To be honest, so several of us have spent time trying to see if we can make more general examples of solutions to this. We can't, but there could be some interesting halfway houses. Let me give you an example of a halfway house. Suppose I just declared that I want the complex structure to be I want this to be 0. I want it hypercalar. So I want this to be true. And I want this to be, I don't want to have beta depend on V. It is still then possible, at least in principle, that maybe you could let DS4 depend on V. In other words, one of the thoughts I had, but never got it to work well, was, okay, this DS4 is a hypercalar manifold. So maybe what I can do is I can take a hypercalar manifold where its moduli depend on V. And then I can have maybe the given talking points move as a function of V. And I tried to implement it there, but it didn't work. So this is a piece of territory where there's probably you may not be able to solve the full problem, but there might be some interesting physics in some restricted class of problems. But what you're looking at now is a family of metrics, DS4 squared, that depend on V. So you've got this foliation of hypercalar metrics in some sense, or nearly hypercalar metrics. And so is there a clever, interesting foliation of hypercalar metrics? And as I say, one of the ways that one might be able to do that in an interesting way is to take the standard hypercalar metric at constant V. It's just some Gibbons-Hawking space with Gibbons-Hawking centers. And then you let those positions of those Gibbons-Hawking centers depend on V, so that there's a momentum wave in this thing, which is where the centers of the Ford geometry oscillate backwards and forwards around an equilibrium position. Maybe you could do that. I don't know.
You mean like perturbative, like some type of perturbative thing? Small oscillations around.
Okay, you could do it. That might be a good way to start it, but more by doing small oscillations. But physically, what we know about these multi-center solutions is that when you put fluxes on bubbles, the fluxes tend to hold the bubbles up, and the gravity tends to collapse the bubbles. So if you slam some flux on a bubble, and you imagine hitting the Gibbons-Hawking point, moving it in, pushing it in. If you push it in, what are you doing? You're trying to compress a magnetic flux into a too small a volume. It doesn't want that. It wants to push out. So there should be a dynamics here where you move a Gibbons-Hawking point in a little bit and let it go, and it will oscillate around its equilibrium position for all time. Now, if you can make it oscillate as if it were a left movement momentum wave, that would be a whole new class of superstrata.
The main problem is if you do that naively, you think you're losing supersymmetry, because if you would just do it, if you make it time dependent, it starts oscillating, but it's just going to be non-supersymmetric. So you can throw it the whole ansatz. You have to do things from scratch.
Except you can make this depend on V, not on you, not on time. And so maybe you could make an interesting left moving momentum wave where you start with Gibbons-Hawking here, allow the moduli to depend on V, and find some extremely clever way of just solving these system of equations. Maybe you have to actually invoke the full force of this, but the starting point should be that every fixed V slice, it's Gibbons-Hawking. To be honest, I haven't tried running with that idea. I've sort of thought about it, but there's probably some really cool physics. But the one thing that's been an incredibly useful guide to us in finding our way through the system and solving it is our friends, Stefano and Rodolfo Masaki, who basically come along, on David Turton, and say, look, here's what the holographic field theory is telling us you need to activate in the way of degrees of freedom to describe this particular scattering process. And then we turn those fields on and we find a whole new class of things. But there are so many degrees of freedom in this system that finding the interesting one, finding the one that describes some interesting holographic physics, is probably the right guidance. As I say, Masaki, I think it's Masaki and Stefano and maybe Nate as well, have got some interesting discussion about how to deform this metric to produce interesting new states. As I say, the superstrata we've built are these really naive, stupid ones. Where's it gone? The naive, stupid ones where we just start with R4. We just start with flat R4. What Nathan and Masaki and Stefano and Rodolfo are telling us is there are interesting ADS CFT, well, CFT states that move you away from flat R4. And there are some that keep you in flat R4 that we haven't done, but there are some that move you away from flat R4. Understanding what those are, then maybe making them V dependent, that would be amazing, but it will throw you into that class. So all this to say, if you just try and cold solve the mathematics that I've described, it's like this problem where the devil whispers in your ear and you go away and you disappear for weeks at a time, and if you're lucky, you come back and eat again. It's a fascinating problem, but I think the real way into that is you take some of the things our friends who do the CFT side of this and look at the dual of those states and try and make them V dependent, because they should be, again, if you're BPS, it's all about left moving momentum waves. So there should be a BPS version of left moving momentum waves. So I'm going to, as I say, be solving the left moving momentum wave. One thing I'll just throw out there to sort of, again, to dangle in front of Bogdan is everything I said with respect to V, it's a completely convention choice. I could have made it with respect to U, because I'm talking about, where's it gone? Yeah. So there is a symmetry in this formulation in terms of V and U. I can just exchange U and V, and in fact, it's just completely trivial inverting the orientation on the Y circle. Where's it gone? I don't know. I've lost it. Yeah, just flip. U and V are flipped by saying Y goes to minus Y. And so, you see that omega and beta then, roughly speaking, interchange, and there's a symmetry in this entire beast. So there is a way to recast left-moving or right-moving momentum waves in a very natural way. And the only reason why U is slightly asymmetric in here is that it's a null coordinate and it's been chosen to be the killing vector. But you could equally well chosen V to be the null coordinate and then written it in terms of, and said that was a killing vector and so forth. So you can trivially flip all of this and describe right-moving momentum waves. And so the other cool thing to try and do is to try and take this system and simultaneously set up colliding left-moving and right-moving momentum waves. We're going to describe the whole point about superstrata is we've just picked an orientation, left-moving, and we're going to build the holographic jewels, the gravity jewels of those momentum waves.
Thanks.
You're welcome. Any other questions? Comments?
Yeah, I have a question about so like, does the adding using a different base and just introducing V dependence, are these completely different directions or they're somehow related? Like,
no, okay. So if you add, if you just take a new base, make it arbitrary hypercalar, then arbitrary hypercalar is already tough. The easiest to do is Gibbons-Hawking. So you now replace, the Gibbons-Hawking sort of space, ALE spaces and so forth.
Right.
Okay, so in this thing, the thing that's hidden, but it's in my lectures from last year, is that the base is now allowed to be ambipolar. What that means is that, let's see, let me get to the 5-dimensional equations. 5 dimensions. Oh, lost them. Where are they? I had some reduction. Oh, there it is. I've missed it. Reduction 5 dimensions. So the point is the base manifold here is allowed to be ambipolar, which means that the metric can change signature. The four-dimensional base metric can change signature, because it turns out you can do that and still have a good Lorentzian five-dimensional smooth manifold. So that means that you're allowed Gibbons-Hawking spaces with positive and negative charges, and so it's easy to make it asymptotic Euclidean because you just get the sum of the charges being 1. So there's a whole technology, and I described that in my lectures from last year. So what do you do then? So now you can have multiple. Let me share a different screen. Screen sharing. I'll start drawing. There we go. There it is. Sketchbook. Okay. So let's edit clear. Okay. So what you can do now is you could now have some base space. This is the R3 of Gibbons-Hawking, and then there's some fibers above it. And the sort of canonical picture you can draw is that if you have Gibbons-Hawking points, the fibers pinch off at Gibbons-Hawking points, and so you get a sort of 2-cycle here, and you get another 2-cycle here, and so forth. These are usually called the bubbles. Okay, so you can make the whole point about hyperkähler is you can have now non-trivial 2 cycles, or when you uplift to 6, they become 3 cycles because the U1 fiber gets fibered over the 2-cycle. So now you have these things with multiple bubbles. But if you stand off at a large distance, at infinity, if you like, you make it asymptotically ADS3 rather than asymptotically flat. You stand off at a very large distance. It's the D1, D5 CFT. So the mother of all things in the UV is the D1, D5 CFT with central charge 6N1, N5. But in the middle of it, you've got this piece of topology, all this stuff, all this bubbles. And those bubbles should represent some new phase of that D1, D5 CFT, some new infrared structure. We have no idea what it is, but what you can imagine doing is, oops, my pen is doing something weird, is running a momentum wave around this bubble and a different momentum wave around that bubble, which in principle is possible. You'll see that the momentum waves are nothing other than shape fluctuations of the bubbles. This is what we'll discuss later.
So those actually can be constructed, I think, analytically, using your method from the paper with Ben Niehoff.
There are some, yes, okay. There are some limited examples where you can do this and explicitly. But there is some correlation between the momentum wave you put here and the momentum wave you put here. So what's the picture I'm selling you? What I'm trying to sell you is that at a long, long way out, you have a D1, D5 CFT with a very high central charge. In the middle of it is this complicated phase, which is described by multi-bubble solutions. We don't know what the holographic dual of that is, but you can still ask the question, can I put a momentum wave on each and every bubble? And I think the answer is yes. And I think you can put a different momentum wave on different bubbles. So now what I'm trying to sort of sell you is that each bubble is maybe some kind of CFT in its own right. When it meets another bubble, it's interacting with that CFT. And each of those CFTs can have momentum wave excitations. That I think is a possibility. Computationally, this gets kind of nightmarish because remember, to make the superstrata, to make a multi-centered bubbles, solve the superstrata, you have to start solving Laplacians on the base manifold. And now to solve it on a generic Gibbons-Hawking manifold where it depends on the fiber, it's getting hard. It's not, it doesn't mean it's impossible, but again, it's one of those things where 1 or 2 illustrative examples is probably immensely valuable. Then you can actually, try and pull together what the big picture is. But even at the first step, I don't have the guidance of the ADS CFT. What's a multi-bubble solution as an infrared fixed point of the CFT? That if you can answer that, I'll buy you a huge, really good bottle of wine. If you can tell me the answer to that. I'm serious. It's Bulgarian. Sorry?
Rakia. He's Bulgarian. He doesn't drink wine. He drinks heavy stuff.
Okay. Okay. A good bottle of scotch then. but seriously,
let's go with Irish Rakia. It's fine.
But it's an important problem. But in fact, going to arbitrary hyperkähler bases is something I really want to try and do. I have some ideas about how to do this. There are techniques for probing these geometries. But it's the issue also here is this phase space is huge, And there are many, many places you can start looking at solutions. The question is, what are the interesting ones? What are the ones that are going to teach us some really new physics? And I think the very first thing here with this class of problem is to understand what the infrared phase is without the momentum excitations. But, you know, I'm agnostic on this. If I manage to make a solution where there's a big momentum wave here and another big momentum wave here, and I stand off at infinity, I can say, well, okay, what does that look like as an excitation of my parent CFT? Maybe by putting momentum waves on bubbles, I can get some insight into what the infrared phase is in the middle by looking at it, where it must have come from as an excitation of the UV CFT.
Mm.
Right. I mean, these are all really interesting questions. I mean, so the technically hard level of this is, how do you solve, you know, the kinds of things you've got to start solving are things like d of z, or I'm probably going to get this wrong, is equal to d of theta or something, theta. Actually, it's covariant d, and I need to put a star here. You have to start solving those equations on this given talking base.
Right.
R4 is easy because you can separate the wave equation and away you can go. But having said that, remember it's a hyperkähler geometry, and there are lots of useful mathematical techniques for generating modes on hyperkähler geometry. So there might be some clever way through using explicitly the hyperkähler structure.
All right.
Okay.
I have one more much more basic question. So, like, you kept saying that the first layer of BPS equation, it's feeding essentially the sources of the second layer, right? But
yes.
But so you also mentioned that like in the first, like, it's the geometry and the first layer BPS equation. What do you mean by geometry? At that point, you don't know what the geometry is. So
okay. The base geometry. So I've tried to distinguish it, but I probably flew by too fast.
Yeah.
So let's go back. Let's go back to the various layers. Okay. So BPS conditions. First and foremost, okay. Let's just see. Back it up. So this is why I sort of started with n equals 0. So we started with n equals 0, and we asked what is the geometry. So what we learn at the 0th layer is what is this 4-dimensional geometry, and what is this vector beta. That's what I mean by the 0th layer. So the whole thing we've discovered about the BPS equations is it tells you to solve the problem in layers. And there's going to be, in this situation, there are actually only 3 layers, the 0, 1st, and 2nd. And the 0th layer is you settle on this geometry, and you settle on this beta. And this geometry is so-called almost hyperkähler, and this beta has to satisfy this condition. So it's really about ds4 squared and beta. So when I say the 0th layer, I mean that. Then there's going to be all this other stuff. There's F, and there's omega, and then there's the fluxes. So the first thing you have to decide, which is the nonlinear discussion, because this is a nonlinear equation, is that these things are what they are. And in particular, if you take the simplest choice, which is the coward's way up, but that's all we can do, we make it hyperkähler, and then we know what we're doing, and we make beta self-dual. That's the sort of 0th layer. You've declared what I call it the geometry, but I mean the ds4 squared is going to be.
So in a way, the 0th layer is a choice that makes calculation possible, and that's it for now.
That's it. But we do know what the most general possibility is, thanks to the work of GMR.
Right.
We know it's going to be this, but for practical reasons, we make a choice.
Yeah.
And then the hard, heavy lifting is to figure out omega and F and all the other pieces of the thing. So then there are all these functions that turn up in the fluxes. And so these are the electric charges and the magnetic fluxes and so forth. This is all the magic that is actually going to make the superstratum smooth, and it's going to give you the electric charge of the background and so forth. Yeah. So it is actually a very important point that maybe gets lost in this discussion because we're focusing on superstratum construction. Let me cut to the 5 dimensions. 5 dimensions. It gets lost in the discussion, but I try to sort of bring it out in the previous thing. If you just go straight for a black hole, actually, let me do that. Go straight to the black hole story. If you go straight to the black hole, so basically for the black hole, everybody in sight is a harmonic function, but it's got a source, a very singular source, and that's what gives you the horizon and what gives you the singularity in the middle of the horizon. Right. Once you form a horizon, you get a singularity. So choosing a singular source is not going to make you a microstate geometry. But if you don't, but here's the important point about the five, it's easy, most obvious in the 5-dimensional story. So now what happens is you say, I've got the obvious option where I choose a singular source and make it harmonic. But there's another option, and this is the option that's given to you by microstate geometries, is you say, no, I can, as Joseph would say, that you dissolve the charge source in magnetic fluxes. And so now you can put cohomology onto the base and put magnetic fluxes onto the base, onto those things. And then this can source electric charges in a smooth manner.
Right.
And so the whole electric field, magnetic field story that underlines superstrata it's buried there, and I've hidden it in this discussion. But really what's going on is you said, I want to desingularize the black hole and remove its horizon. To do that, there's a theorem that Gary Gibbons and I proved, admittedly only in 5 dimensions, but it basically says the only way you can do that is you have to replace any electric sources you've got by magnetic fluxes on cohomology cycles.
Okay.
And so that's how, this is the magic of how, so if you remember, I'm going to go through that next time when I talk about the K-Kulitzki monopole. The magic is you start with a singular source, a singular black hole, and say, okay, let me add some degrees of freedom that desingularize it. And the easiest thing to do with a 2-charged black hole is you add a Kulitzki monopole moment and an angular momentum, and suddenly you've just got this beautiful supertube solution, which is AdS3 times S3. For black holes, it's the same story. You replace these singular sources by magnetic sources that are cohomological, and away you go. For the superstratum, it's going in a slightly different direction. You don't add more topology. What you do is you just have one bubble, one flux with a self-dual answer, and then you add a traveling momentum wave to it. And that's enough to get you the 3-charge solution. But there's a big, fat cohomology cycle that's holding your solution up and stopping it collapsing into making singular solutions.
Or before the momentum appears.
Yeah, in fact, so there's a reason why we do that. And the reason is because it's all because of the guidance we keep getting or get from our friends who do the D1, D5 CFT. And so the starting point for the D1, D5 CFT is the Ramon ground states. And those are holographically dual to particular classes of supertubes. So what we do is we say...
That's very simple geometries. I mean, they're essentially AdS3 times S3.
And so that's the tack I'm going to take next time. I'm going to say, let's start with first the black hole, and let's now let's look at the underlying field theory. Let's add the Kulitzki monopole and make the fundamental supertube, and then we're going to add momentum waves to that. And when we add momentum waves to that, we get the superstratum. It goes in a very different direction to this, but there's nothing, just, these are in some sense 2 orthogonal axes, but there's a whole space in between where you could imagine adding multiple bubbles and adding momentum waves to each of those. And that would be a beautiful and wonderful thing to do.
Right.
It's just hard, but because the more bubbles you add, the less symmetry you've got, roughly speaking.
Right.
And R4 has and AdS3 times S3. You want to add a momentum wave to that. You've already got a transitive symmetry. It's still heavy lifting, but it's much easier than doing anything in a more general Gibbons-Hawking space. So the reason why there are many reasons why we started doing superstrata, but one of which was simply we started asking ourselves, what's the holographic gravity dual of the Strominger alpha microstates? And we realized that in the D1, D5 P system, there had to be these things that we called superstrata, and then we set about constructing them.
Right.
And so this structure, this 5-dimensional story, was guided by what the hell else can we do that gets rid of black hole horizons and horizons and singularities? Well, we found this. But then the other axis we've been pursuing is what are the holographic duals of this known D1, D5 P CFT? And that works very well. And now there's this incredibly large phase space in between that we would love to fill out.
Yeah.
And the number one question, I'm not joking, I'll get a nice bottle of Talisker Scotch or a couple of bottles of wine. If you can tell me what the holographic dual of a three-centered solution is, I will be ecstatic.
Okay.
Three centers. Five.
Sorry?
Even 3 centers, I mean,
Three centers is
4,
fine.
5,
Yeah.
6, no. We can do those.
If you can put them on, you can even put them on the same axis.
Okay.
There's got to be got to be an answer to this question, and as I say, it's got to be an answer that comes from the D1, D5 CFT, because remember, one of the things we learned from holographic field theory is that if there is a UV CFT, and then you add to it the non-normalizable modes drive you in directions of holographic flows, but fluxes, these kinds of fluxes are normalizable modes. And so therefore they represent states of your
right.
your D1.
You're still in the same CFT.
You're still in the same CFT, and these fluxes and multi-centers must represent states of the in some infrared phase of the system.
Right.
What is that phase?
Yeah.
Even for, so long as it's got, two centers, we know the answer. It's the super tube. It's the but
yeah.
But 3 centers, we have lots of thoughts about this and lots of clues. But any answer would be very much appreciated.
Right.
But the other side of the coin is holographic field theory tells us these have to be phases. It simply says, look, there's this thing that is a set of normalizable modes excited inside inside a UV field theory, and there's the normalizable modes. They turn them on, and there's this solution which is smooth, macroscopic. According to all the laws of holographic field theory, it's got to be a phase.
Yeah.
There's a homework problem.
Great.
Any other questions, guys?
I'd like to push back on this statement that the only ones we know how to do are where the base is R4.
Okay, go for it. Yep, sorry. Yes.
I mean, so we can spectrally transform these to 2 centers Gibbons Hawking, right? And then this makes it clear what the bubble is that you need for
okay, so
topology.
Absolutely. So what Robert says is absolutely correct. So I've hugely oversimplified, and I'm glad he pulled me up short on this. So morally speaking, what we can do is any 2-centered solution. Now, what does that mean? We're going to see this next time. But basically, in R4, there's the center of space. So that's one center, the origin of space, where we use the center of our coordinate system. There is also a second center that's going to turn up next time, which is where we choose to put the supertube. So really this thing, or you can think of another way, you can think of it as saying the fundamental configuration that we're going to start with next time is a supertube which has a locus, which is a ring in R4. A ring in R4 can be described by spherical bipolars, and we're going to go through this too. A spherical bipolars, it's a 2-centered coordinate system, and so spheroidal coordinates, I think it's called. So morally speaking, the fundamental starting point we're going to deal with is really a 2-centered spheroidal coordinate system. And I'm choosing to describe this as starting with R4, where there's one center, and next time we're going to put a second center on, which is where the supertube is located. So hidden in that is a 2-center space. Now there's a whole bunch of coordinate transformations and spectral transformations where you can turn those centers into things that don't look like they start from a single R4. And Robert's absolutely right. Any 2-centered Gibbons-Hawking space with plus charge and minus charge can be mapped onto R4 and a supertube.
Or R4 or MOSI5.
Sorry? Oh yeah, there's an orbifold.
But
So buried in this discussion, there's a fair bit of some technical expertise. So this is why I was very careful to say the uncharted territory is 2 bubbles or 3 centers, because the phase space I'm working in here is hidden 2-centered, and I'll make it much more explicit as we go. It really is a 2-centered solution. Center of space and the locus of the supertube will be critical, and you'll see us go straight to spheroidal coordinates. So I think, to paraphrase Robert, another way, is the two-centered solutions we know are ones where you can still adapt spheroidal coordinates to it. Is that right, Robert?
Yeah. The other thing is, I mean, you mentioned this theorem that you need non-trivial topology with flux threading it to get our solutions, right? And so it's not obvious where this is if you use the R4 base, right?
Well, it sort of is in the sense because what happens is that the free sphere never gets small.
Right.
So there is one cycle, one bubble, and it's the three sphere. So the point is the three sphere around the horizon. So yes, you use an R4, but what happens is in the R4 is that as usual when you put a big stack of brains at the origin, what happens is that R is 0 or rho is 0. I think I wrote this here. Rho is 0 is the horizon, and what actually happens is you get a big fat R3, and there's the bubble. So this set of lectures is sort of orthogonal to the other set of lectures because the other set of lectures talked about how to bubble space-time. There is a bubble here, it's this big fat sphere, and it never gets small. And we're always going to be outside the horizon region, so rho is always going to be positive, and so therefore this is always going to be big and fat. Did I answer your question?
Yeah.
Yeah. If you want to make more comments, he's keeping me honest, which is great. Any questions or comments? So I am still while I'm trying to show you the technical details, I'm still trying to I'm still hiding things, or at least trying to approach it in a way which is as simple as possible. So we're going to work with R4 and we're going to put another center in, but you're going to see spheroidal coordinates turn up very quickly. They're actually in the notes but at the moment, but they're not in this presentation. So two-centered can be done in any setting. If the minute it becomes three-centered, that's when you break the symmetry, you break the separability, and you are having two non-trivial topological bubbles. And then I don't know how to do it. Any other questions or comments? Nothing? Okay, so there won't be one lecture next week. I'm taking a vacation, but there will be one the following week. And if this time works for everybody, then let's just keep it at Thursday at 2 o'clock, unless Rencontre gets in the way, and then I'll move it to the earlier or later, depending on what happens. Yeah, we'll keep it on Thursday, I think, and we'll just do it earlier or later, depending on Rencontre. But let's keep it nominally at 2 o'clock in the afternoon. And as I say, if Rencontre gets